All right, we're moving around the hydrologic cycle and we're at the atmosphere. This is that envelope of gases that starts out basically air in the soil, air in caves, and goes up to 6,000 miles above the Earth's surface. Here is our hydrologic cycle. We have moved around a bit on the ground and we've taken water down to the sea. We've transpired water out of our leaves, the stromata, and now we're up here in the clouds in the atmosphere. The evaporation and evapotranspiration of moisture from the land surface enters our atmosphere, and then over time, as it cools, it's going to condense into clouds. When those clouds and water droplets get heavy enough, they're going to fall back to the Earth's surface as precipitation. All right, the atmosphere is really important to life on planet Earth. It allows for us to have liquid water at the Earth's surface. The actual weight of those gases pulled down by gravity creates pressure, which creates the stable environment for liquid water. The atmosphere also absorbs solar radiation, warming the Earth, so it keeps us warm here. That warming in the atmospheric gases also insulates the Earth, and our airflow moves heat around the Earth. Remember hot... I had to shoo some people outside. The equator has a direct sunlight, and so it heats up, and so airflow, those cells where the hot air rises and cold air sinks, we're moving warm air towards the poles and cold air back down towards the equator. So the atmosphere is very important in that. If you want to study more about the atmosphere, you could be an aerologist. Aerology is the study of the atmosphere. All right, the formation of the atmosphere. The Earth formed 4.6 billion years ago, and there was a point when the Earth was pretty much molten. The lighter elements that were in that planet Earth then rose to the surface. That's how we have the crust, mantle, core with different chemical makeups. So the hydrogen and the helium were released into the atmosphere during that differentiation and the molten Earth. Later, so we have lots of volcanic eruptions. These volcanic eruptions release water vapor and other gases like nitrogen, carbon dioxide into the atmosphere. So creating the atmosphere we have today that is very, very nitrogen rich, right? 7 to 8% nitrogen. About 2.4 billion years ago, cyanobacteria. These are photosynthetic bacteria in a symbiotic relationship with blue-green algae. They began photosynthesizing and creating our oxygenated atmosphere. That was the first major change in the chemistry of the atmosphere, was that oxygenation event. The next biggest change in our atmosphere is happening now. That is humans and our industrial processes creating air pollution. We're adding carbon dioxide, and we are now the pushers of atmospheric change. All right, let me turn this off. What's our atmosphere made of? It is, like I said, 7 to 8% nitrogen. It is 20.9% oxygen, almost 1% argon, a bit of carbon dioxide, and then other elements like neon, helium, nitrous oxide, methane, ozone, and trace gases. So there's the pie chart there. It can really make you realize it's mostly nitrogen and oxygen with these other add-ins. The add-ins are very important though. They're small amounts, but they have a big effect on life on Earth. I threw in this picture of me. I got coerced into becoming a scuba diver, and that tank there on the back, that white tank, during scuba diving, you have to mimic what the Earth's atmosphere is because that's what your lungs are used to. the pressure and the chemical makeup. So if you scuba dive, the understanding of this becomes really important. Okay. Small amount, big importance. Those trace elements like carbon dioxide, water vapor, methane, they make up a small percentage of the whole chemistry of the atmosphere, but they have a huge act on regulating the Earth's temperature, making life on Earth possible. Those are the greenhouse gases. Without these, the Earth would be too cold for life to evolve as we know it, right? Maybe we would just all be, I don't know, Arctic creatures. So those greenhouse gases provide that warmth. In the figure here, we have the greenhouse effect. The sun is beaming down on us. Some of that sunlight hits the earth and is reflected back, and some of it becomes heat. Carbon dioxide and the other gases in the atmosphere trap the heat, keeping the earth warm. Water vapor is one of these greenhouse gases. It, along with the ocean currents, moves heat, like I was saying earlier, from the equator toward the higher latitudes towards the poles. There's another gas in the atmosphere called ozone. Ozone is O3. So normal old oxygen is O2, but ozone is O3. It absorbs the incoming UV radiation from the sun. What that does is allows for us not to get big sunburns and skin cancers, right? From too much sun exposure. You should still protect yourself from the sun. Another thing in the atmosphere is aerosols. These are little bits of suspended liquids, solid particles like dust, maybe blown off of our deserts. Volcanic eruptions send aerosols into the atmosphere, and eventually gravity is going to pull all these little droplets back to the Earth's surface. But while they're in the atmosphere, they play an important role in the hydrologic cycle because they are surfaces on which water is going to condensate and become clouds. So pretty much every raindrop has a little bit of dirt in it, right? Some aerosols are bad because they lead to acid rain. The image below shows some of the different inputs of aerosols into the atmosphere, whether it's from plankton, sea spray, dust from the deserts, particles from forests and grasslands, VOCs, smoke from wildfires, and then sulfates from, sulfur dioxide comes out of a volcano, and then in the atmosphere it turns into sulfate. So those can become sulfuric acid. That could be bad. Okay. Here we're going to talk about the layers of the atmosphere. What I want you to mainly see from this diagram is what defines the different layers. So we are here on Earth's surface, and the troposphere is that first layer. It is about 10 kilometers high from the surface to the top of the troposphere, and it represents a zone in the atmosphere of cooling. So look over here at the graph. The troposphere is going to be a zone of cooling, and then once we get to the stratosphere, this is where let's see, we have commercial jets, spy planes, weather balloons. This is a zone of heating, so this heats up all the way to 50 kilometers, and then the next zone is the metasphere, and that is the zone of cooling again. So the need to remember here is that the different layers of the atmosphere represent zones of cooling, warming, cooling. All right, so here is about let me see on those dogs. Okay, the troposphere. This is the layer next to the Earth's surface. The Earth's surface warms the base of the troposphere, right? And it's going to cool upward from there. As altitude gets higher, there's less pressure on the gases of the atmosphere, And at higher elevations, then it allows them to expand. So the molecules are further apart, and that cooling is called adiabatic cooling. And the air is cooler, it's thinner. That's why you have to have, well, you don't have to, but it makes you live longer if you have an air tank on top of Mount Everest. This is also where the weather is, vertical and horizontal mixings of high pressure, low pressure, cold air, warm air. The next layer is the stratosphere. This is where that O3, the ozone, comes in. The sun breaks the oxygen molecule there, the O2, into O, and they are going to recombine all the free O's with the O2s to form O3. So ozone, the ozone layer of the Earth is in the stratosphere. The temperature increases in this layer with altitude as the ozone that's created there absorbs UV radiation. So remember, the troposphere is defined by cooling, the stratosphere is defined by heating. Volcanic ash and human-made pollutants can get up into the stratosphere and stay for a very long time. The next layers above the stratosphere is the mesosphere. The mesosphere is where we see shooting stars or meteorites or meteors coming in and glowing. Rockets can go that high. In this layer, there's some mixing with cool air and that warm air coming from the stratosphere. So it is cooling off. Above that is the thermosphere. This is where oxygen, it's going to heat up again. This is another heating layer. Oxygen molecules absorb shortwave UV radiation and heating occurs, but that's not even on the diagram, so don't worry about that. Okay, last slide here. On the left is a link to a very short YouTube video. Let me turn my face on. The one on the left is a very short video on rain. Basically, the sun heats up surface water, and that surface water then is going to evaporate into the atmosphere and then condense in rain droplets and fall back to the earth from clouds and precipitation. That's the gist of the rain one. This one here is precipitation link. That one's a little bit longer. It goes into the different kinds of precipitation. So the same idea as the rain link, but this one just expands on it a little bit more. Talks about frozen precipitation, mist, and droplets, and a little bit about fog. And then the last link is just a funny little thing for you to listen to as you study the atmosphere.